Hello and welcome back to the final installment of a four-part series on how to control the Quanser cube rotary pendulum using Collimator for modeling, simulation, and controller design. In the previous videos, we looked at linear control for regulation and stabilization, as well as a simple nonlinear control strategy for the swing-up problem. This time we're going to look at a couple of more advanced strategies. First, trajectory optimization, and then we'll see how to train a neural network feedback controller that can do the swing-up task. So the neural network controller is a little bit more bleeding edge compared to other kinds of controllers we've looked at, but we're excited to show it for a couple of reasons. First, it gives pretty impressive results on the hardware, even compared to a tried and true strategy like feed-forward control. And second, we think that this kind of hybrid machine learning controller where you combine a neural network control law with more traditional discrete control logic or filters or whatever, and then train it using differentiable simulation could be an important category of control architectures in the near future. On top of that, if anything, it's easier to set up than something like trajectory optimization and definitely takes a lot less analytical effort than something like energy shaping control with partial feedback linearization as in the last video. So let's start first with the trajectory optimization. Where we left off with the energy shaping control was noting that it didn't really generalize very well to other kinds of systems, and it didn't allow us to directly enforce any constraints. It's also not a very aggressive controller in the sense that it takes a while to sort of swing back and forth and do its thing. And for applications like robotics or aerospace, we want to be much closer to optimal, however you need to define that. So the idea of trajectory optimization is to numerically solve an optimal control problem, like, for example, this one. If you've been following the videos so far, this probably looks familiar from the LQR cost function, this term here. And the main differences here are that now we're looking at a finite end time instead of integrating to infinity. We're going to use the full nonlinear dynamics model instead of the linear approximation. We added a terminal constraint. So these might not seem huge, but it's enough that there's not a general analytic solution as in the LQR case for an infinite horizon. Instead, we can find approximate solutions using different methods from numerical optimal control. Basically, what we'll do is discretize this problem and solve it offline ahead of time. This is also sometimes called path planning. A particular popular approach to this is called Hermite-Simpson direct collocation. And in that, we approximate the state trajectory as a piecewise cubic polynomial with a piecewise linear control. We'll add a link to the video notes if you want to learn more, but in Collimator, this is easily accessible with the trajopt function. So to set this problem up, we need state and input weight matrices, time horizon, terminal state, initial state, and there are more options available in the trajectory optimization function that we're not using here, including various kind of other bounds and constraints. This sets up a fairly large constrained optimization problem. So once we set this up, Collimator calls out to ip.opt to solve the nonlinear problem. When it's done, then we can plot the optimized trajectory and even do a quick animation to see what the planned trajectory looks like. So already this is looking like a much more direct solution to the problem compared to the energy shaping control we saw last time. However, not only is this trajectory computed based on the idealized model, it's also computed using this sort of collocation discretization, which is not even the same as what we run in a forward simulation. So we definitely need to see what happens when we try to execute this. And right now this is going to be fully open loop in that we just give the specified sequence of voltage commands and hope that it does what we want. So what we do is interpolate the planned control commands and then use the Collimator diagram builder functionality to put together a simple block diagram. And then we can hook up to the Quanser hardware abstraction layer block and see what happens on the hardware. So unsurprisingly, this doesn't actually follow the path we were hoping for it to. It's possible that we could either use higher order splines or more collocation intervals to get a better match, but realistically, this is going to be pretty typical. For complex and especially unstable systems, the open loop control probably isn't going to cut it. So instead, what we can do is something like feed forward control using the pre-planned trajectory as kind of a nominal path. But this starts to get into some more advanced usage of the Python package, and I don't want to spend too much time in code in this series. So we'll release a tutorial notebook that walks through how to build that up. And these features are also coming soon in the app. But for now, let's turn to a totally different architecture of machine learning control. In the previous videos, I didn't really take much time to explain the controllers since they're so well known that we could just link to more thorough explanations. But this time around, I do want to give a little bit of background because the way that we develop and train this controller is going to highlight a combination of features in Collimator that's a little unusual in either a pure machine learning or a pure simulation framework. So the basic setup for the neural network feedback controller is going to be something like this. I'm adding a MLP block for multi-layer perceptron or fully connected feed-forward net, whatever you want to call it. We can fully customize this over here with different sizes and activation functions and so on, and including uploading a pre-trained model if we want to do that. So we'll take the output of the plant in the simplest case and then compute a new control and feed it back and advance the time forward one step. And actually, in order to make sure that this is actually a discrete controller like we would run on the hardware, we would also want to drop a zero order hold block in so that the MLP only gets sampled at discrete intervals. So usually we'll also kind of help to inject some noise into here, which will sort of tend to regularize the policy gradients. And then we'll also add in an objective function that could be basically anything you want. We'll end up using something that is similar to what we did for the trajectory optimization, so some running cost that gets integrated over time. A typical way to train this neural network would be with some kind of reinforcement learning algorithm, which kind of generally speaking, reinforcement learning can be thought of as sort of a Monte Carlo method for optimizing a feedback controller where we run a bunch of simulations and then compute a quantity that converges in expectation to something we can use to improve the performance of the controller. And there are enough different kinds of RL training algorithms that it's hard to speak to generally here, but as a very simple example, this is kind of close to the reinforce algorithm. So you do a bunch of simulations, randomizing some inputs, and then compute a quantity that converges in expectation to the policy gradient or the gradient of the objective function J with respect to the neural network parameters theta here. And so this reinforcement learning often works really well, but it is famously computationally expensive. So what we're going to try to do is take advantage of the fact that the entire simulation in Collimator is differentiable to directly compute the gradients of the objective function in a way that's hopefully more computationally efficient than standard reinforcement learning. Although, of course, we can still introduce some randomness here if we want, and again, that often helps to kind of regularize the cost landscape. So most simulation tools aren't differentiable and can't do this. And what does that mean? If you're familiar with the basics of neural network training, you might know about the backpropagation algorithm, which efficiently computes the gradients of all the neural network parameters if we have a single scalar output function. And the way the differentiable simulation works is pretty much the same. So what we do is run a forward pass, which is the normal simulation forward in time. And then as you do in backpropagation, we have to go backwards in time to the beginning in what's called an adjoint simulation. And the results of both the forward and adjoint simulation combined can be used to compute the gradients we're looking for in an efficient way. And in Collimator, this simulation can include fully hybrid dynamics, including periodic discrete updates, state machines, guard reset maps triggered by collisions or something like that. It's very flexible and, again, fully differentiable. So with that in mind, let's head back to the app and fill out our controller architecture a little bit more. So I switched to a pre-built model here since this is starting to get a little bit more complex. So starting from the outputs of the plant, which again are going to just be the angular position measurements from the rotary encoder. The first thing we'll do is offset this by 180 degrees in the pendulum arm position so that 0 is the reference position. And then, as in the other controllers, I think we kind of expect that having the angular velocity measurements as well might help us design a better controller. So we're going to augment the measurements with a filtered discrete time estimate of the derivatives of the signal and mux those together. So we'll have a length 4 vector that we pass to the neural network controller. Again, we're going to inject some noise here and then do a couple of simple modifications, make it a scalar signal, and also use a step function to effectively hold the control at 0 for a specified amount of time at the beginning, which kind of helps the hardware get equilibrated at the beginning. From there, again, we want to make sure that we add a 0-order hold block on the output so that the controller can only be sampled at discrete times, as well as a saturate block so that when we're training, the network knows that there are going to be hard limits on the voltages that it can output. The actual system can go, I think, to plus or minus 15 volts, but I'm going to be a little conservative here and say plus or minus 10. We can also add in rate limiters, other discrete filters, state machines, or whatever you want. And then the cost function, again, is going to be very similar to what we did for LQR, just a quadratic sort of regulator cost, and then integrated in time. So let's just run this once to make sure that everything compiles, although we don't expect that this is going to actually work very well because the neural network hasn't been trained. We just want to make sure that it runs and that we get a valid time series. Okay, good enough to start with. So now let's head back to the code and see how we can train this neural network. All right, so now that we have our model all set up, we can customize our training algorithm in Python, similar to what you might do with standard JAX, PyTorch, or any other machine learning framework. I'm not going to go this line by line, but we'll have a link to the code in the video notes if you want to try it out. I just kind of want to give a basic idea of how you can use the Python package to customize some of the optimization problems we're trying to solve here. So there's basically two parts. And the first is a helper class called a trainer that pretty much tells the optimizer how to interact with the Collimator model. So for instance, we have to tell it what parameters in the model are optimizable. In this case, we're just using the neural network parameters. But you could grab pretty much any of the parameters that you're able to modify in the app out of here and optimize them in this same way. Then we have to tell the trainer how to get the models ready for simulation, including any kind of initial states, in this case, modifying the random number generator and adding in initial state that we're going to randomize for batches. Finally, then we have a function to evaluate the cost at the end of a simulation. So you can customize any of these for your specific model. The second part here is a training function where we do a little bit of initial configuration to set up randomized sort of batch training data, you might say, and configure the simulator. Then the trainer can run itself. This uses in the background Optax and other tools from the JAX ecosystem. So that's the basic idea. And going to a notebook, we can pull the model from the cloud to our local machine, and we're ready to train. So just as in the previous videos, we first need to set up our API tokens, and then we can download the project, which will let us extract the specific model that we want to optimize. and then we can go ahead and pass this to our training function and let it go. This will take about 20 minutes to run for 1,000 epochs, which is plenty enough to be fully converged. So we'll take a little break and then come back to test it out. All right, so our neural network training is done. So let's first see what it's able to do in simulation. At the end of the training, I saved the optimal parameters so that we could reload this without rerunning the training. And let's first see what we can do in simulation. So I just have some basic functions here to run a simulation with the optimized controller and then plot the results. All right, so if you look at the voltages here, it's learned a very aggressive control strategy. This is almost kind of a bang-bang controller, switching between the plus minus 10 volt limits, but it's able to very cleanly swing up to just about vertical before starting to fall off. Ideally, we'd love for it to just stay there, but it's not really able to do that. So it does do a really nice swing up and kind of almost balance before falling down. I think it's probably possible to train it, for longer or using different batching, extending the time horizon or something like that. But from kind of a basic point of view, the main difficulty here is that when the error signal or the state offset by the up equilibrium position goes to 0, there's no guarantee that the control signal from the neural network will also go to 0 as it would in PID or LQR, because we have biases and nonlinear transformations and that sort of thing. We could probably train it for longer or do some kind of trick to force it to be 0. But in this case, I would say there's really no point because we also have a perfectly good balancing controller we've been using so far, the LQR. And so all we need to do is drop that in, we'll be all set, and we can switch over to it the same way we did for the energy shaping. So first, let's swap out the idealized plant model for the hardware interface block, and then we can test it out on the real thing. I did that in a different model here. And so the main thing that we want to look for here is that it gets to near vertical. And again, it's okay if it doesn't perfectly balance, since we know that we're going to need another balancing controller anyway. So let's go ahead and run that. All right, and it does get to vertical and beyond. So it kind of matches the simulated behavior reasonably well after, again, a short delay at the beginning to wait for the communications with the hardware to be ready. So let's go back to the app next, and we can reuse our submodels here to build a hybrid swing up balancing controller. Okay, and again, I pre-built this model because this is starting to get more and more complicated. But again, we're reusing a lot from the previous videos. This architecture is actually almost identical to what we did in the last video for energy shaping. We have the offset again by 180 degrees at the beginning, a discrete filter for the full state estimate, and then we pass that for the balancing controller to the LQR, and using the same gains as last time. And now we have our neural network block that we just saw for the swing up controller. And these are switched using a condition defined in a simple Python script block here. And again, the output is held and then saturated as usual. And we don't really need the cost here, but it'll be helpful just to compare. And finally, the plant here is not the idealized model, but we're going to directly go to the hardware abstraction layer block to test this out. So let's pull this model locally with the API and run it one more time to make sure that it'll balance now. There we go. It just actually snaps right into the upright position, smoother even than the trajectory optimization solution, which is pretty cool to see. And this is a fully nonlinear feedback controller rather than kind of a finite time horizon controller that relies on a pre-computed solution that's only valid for a particular starting point. And again, training this is really helped out by the automatic differentiation features in Collimator, which let you create these sort of hybrid machine learning controllers and then efficiently train them in simulation. And this ability to quickly train neural network controllers like this in combination with more traditional control logic is something we're excited to make available. It opens up a whole range of new possibilities for different control strategies and training algorithms. So if you're interested in this kind of thing, I hope you check out Collimator.ai to try out the app and the Python package. So thanks again for checking out this series, and stay tuned for more demos and tutorials coming soon.